To get the most out of this video, you should already know how to correctly name and label the sides of a right-angled triangle in relation to one of the acute angles. Recognise and write expressions for the three trig ratios sine, cosine and tangent, and be familiar with the trig ratio buttons on your calculator. If you're not comfortable with these, I recommend that you watch the first two videos in this series before continuing. In this video, we will apply what we have learnt to calculate an unknown side in a right-angled triangle when we know the size of the angle and one side length. Recall that the whole point of the three trig ratios is that for an angle of given size, such as 30 degrees, the values of the three ratios do not change, no matter how big or small the right triangle is. I have repeatedly used the special case example for 30 degrees, where the side opposite to the 30-degree angle compared to the hypotenuse is always exactly 1/2. So it must be true in this triangle. As long as we know what the ratio should equal, then knowing one of the side lengths associated with that ratio means we can solve a simple equation to find the other. Of course, this case is quite simple and you probably knew the answer right away. But let's use this example to demonstrate a method we can use to find any side for any ratio in any triangle, provided of course that we know one side and the angle. Firstly, you should always label the sides of the triangle in relation to the angle you'll be using. Then we can use our acronym, SOHCAHTOA, to determine which of the three trig ratios match our situation. In our 30-degree example, we clearly know the length of the hypotenuse and we want to calculate the length of the opposite side. The adjacent side is not required in this question. Looking at SOHCAHTOA, we see that the sine ratio uses opposite and hypotenuse. So now we are ready to solve the problem. It's good practice to write the ratio down first, communicating clearly that this is the ratio you intend to use. More importantly, having written it down makes it easier to match the information from the diagram to your expression. Notice that I've written the definition with the opposite over hypotenuse first. You can leave it the other way around if you prefer. I do this so that our unknown side length is immediately on the left-hand side of my equation, where I ultimately will need it to be anyway. It's vital that we transcribe the information from the diagram to the correct parts of the ratio we have written. We see that the opposite side is our unknown a, so we write a on top of the ratio fraction. The hypotenuse is 14 centimetres, so we write 14 on the bottom. And this must equal the sine ratio for 30 degrees, so we write sine 30 after the equal sign. This example is a rare case because we happen to know that the sine ratio of 30 degrees is exactly 1/2, or 0.5. We could have written this instead, giving us a very basic one-step equation to solve. Using the balance method for solving equations, we simply multiply both sides by 14, which gives us this expression. And 14 times 0.5 is 7, as expected. However, if the angle wasn't exactly 30 degrees, let's pretend for a moment it was 31 degrees, then we would need to look the ratio up using the sine button on the calculator. Clearly, this value isn't as nice to write as 0.5 was. Our solution would look like this, and it's quite acceptable. But there's a much neater, simpler way to show the relevant calculations without the need for abbreviating this decimal value. Instead of checking the ratio value for 31 degrees, we simply write that our expression must equal whatever the value of sine 31 is, multiplied by 14. And just like we do with algebraic expressions, we can leave the multiplication sign out. 14 sine 31 means 14 times sine 31. All we need to do now is type the expression into our calculator and we get this answer. Good practice is to show the unrounded value, then the rounded answer. Now let's do one together. Pause the video if you need to get your calculator and pen and paper. In this example, unlike the 30-degree case, there is no chance of simply recognizing the answer. However, we can apply some common sense and estimate that the x value will be more than the 12.3 centimeters, since it is opposite to a 70-degree angle, which is much larger than the remaining angle of 20 degrees. So before I even start, I'm expecting an answer significantly bigger than 12.3. Here we go. Step 1, label the sides. Step 2, notice that the hypotenuse is not provided, nor is it the value we want to determine, so it does not come into this question. Looking at SOHCAHTOA, the ratio must be tan. It's the only one without the hypotenuse. Step 3, write down the ratio we will use. Opposite over adjacent equals tan. Step 4, transcribe the information from the diagram. Opposite is x, adjacent is 12.3, and this ratio must equal the tan of 70 degrees. And step 5, solve the equation. X will equal 12.3 multiplied by the tan of 70 degrees. Typing it into the calculator, we get this, and rounding to one decimal place, we find that x must equal 33.8. At the end of this video, I'm going to show you what happens if the x, the unknown side, is actually on the bottom of the ratio fraction. And it will highlight why this method is so important. First, let's apply our new skill to solve a simple problem. Let's revisit our tree example from the first two videos, but with more realistic information. Here we see that 20 meters from the base of the tree, the angle measured from the ground to the top of the tree was found to be 17 degrees. We wish to calculate the height of the tree. Now, unless the tree is leaning over or on a hill, we can assume it's a right angle here. So we can represent this situation with a simple right-angled triangle. If you'd like to try this yourself, pause the video now. Firstly, I notice the tree height is opposite a small angle of only 17 degrees. The other acute angle must be 73 degrees, so I know the height of the tree will be much smaller than the 20-meter length. Labelling the sides, I again see that the hypotenuse is not required, and I will use tan again. Opposite over adjacent equals tan, so h over 20.0 equals tan of 17. H must equal 20 times tan 17, which equals this. This gives us a height of 6.1 meters correct to one decimal place. Here's one more quick practice for you to try on your own. With practice, we can go through the first few steps quite quickly. Labelling the sides, I see opposite isn't required, so this time I'm using cosine, or cos. X over 47.25 equals cos 36.2. We get x equals 47.25 multiplied by cos 36.2. The calculator does the hard work for you. X must be 38.13 kilometers. If you stick to the method, it should be fine. But now let's see what happens when x does end up on the denominator, the bottom of the fraction. We still follow the same steps. Labelling the sides, adjacent is not involved, so the ratio we must use is sine. Opposite over hypotenuse equals sine. So far, nothing is different until now. The opposite side is provided, and it equals 18.1 centimeters, so it goes on top of the fraction. This means the hypotenuse, x, goes on the bottom of the fraction. It still equals sine of the angle, which is 64 degrees. This is where many students go wrong, especially when they rush to determine the ratio without following the careful steps that I have shown you. Often, they quickly determine the correct ratio required, but they rush to write x over 18.1 instead of 18.1 over x. They will now get the wrong answer. Let's finish the example. When solving equations like this, we first need to multiply both sides by the x. This gives us 18.1 equals x times sine 64. We need to get x by itself. The opposite of multiplying by sine 64 is dividing by sine 64. So we do that to both sides, and this is what we end up with. X is best on the left-hand side, so we can just swap sides. The calculator tells us the answer is 20.1 centimetres, which is larger than 18.1, as expected. Those who rushed and had x on top of the fraction would have ended up with 16.3, which is clearly less than 18.1. A couple of last points. Look at the final calculations for x on the bottom compared to x on the top. The multiplication has simply changed to a division. So if you remember this shortcut, your whole working can be simplified to this. Also remember that fractions mean division as well, so the calculation could be written like this. And this is actually the most preferred, since it's quite neat. It's up to you, or perhaps your teacher has a preference for you to follow. Quickly try this one before we wrap up this video. You should have labelled the sides like this and selected tan as the ratio. This leads to the final calculation, 88.3 divided by tan 40, which is 105.2 correct to one decimal place. One last bonus point. Since this is 40 degrees, then the other angle is 50 degrees. You could have used that, and you would have had tan of 50 degrees. This time x would be on top, leading to this multiplication, but the same answer. Word of warning though, this won't help when it's sine or cosine, because you will simply switch ratios with x remaining on the bottom since it's the hypotenuse. In the next video, we will see how to calculate unknown angles when we know two of the sides.